All right. Okay, I think we can probably begin now. I guess Christmas is coming, and Santa Claus brought you some presents. In fact, he brought you exactly 9 presents. Let me see if I can share the presents with you. The presents are on my website. You can see. Can you see my website right now, guys?
Yes.
Yes.
Great. So here are the presents. And now I guess I'll have to share a different screen with you. Okay, where is it? Okay, can you guys see the file now? There are exactly 9 presents in the file.
Yeah.
Yeah, 1, 2, 3, 4, 8, 9 presents. Yes. This is just for Christmas. In principle, there's more than enough for all of you, I guess, since there are fewer than 9 people in the class right now. Yeah, some presents are about sheaves on the Cartesian side. Some presents are about seeing fingernail rings and sheaves on seeing fingernail rings. And in the last 4 presents, you can also see some homotopy theory mentioned. Let me assure you that the amount of homotopy theory mentioned here is minimal. What you will need is basically formal properties of homotopy limits and colimits, plus a couple of computational formulas. And I hope I can explain them today, but if not, we can talk about it. You're welcome to ask questions. Yeah, so take a look at your presents. Everything is posted on my website. And I guess ho, ho, ho.
Yes, it's very generous. Thank you.
You're welcome. Just as a reminder, our next lecture, and let me now switch back to the other window. Let's see, it's a new share. All right. Our next lecture will be on January 7th, which means there is no lecture next week and the week after that. But you can enjoy your presents, I guess. Let me just copy it here. Yes. Especially those of you who are interested in computing stuff. Eventually, you will need similar techniques, if not completely identical to what I presented in the homework to compute Functorial field series. So in that respect, the homework is geared toward practical computations in Functorial of Functorial field series. All right. Yeah, and feel free to take a look at the homework, ask questions if you have any, and I'm happy to, even though we don't have any lectures scheduled, I'm happy to meet on Sunday or at some other time to discuss the homework. So feel free to email me and we can set up a meeting. Or in case you have questions, I'm happy to answer your questions. Or if you don't even know where to start, we can discuss what notions and ideas from the lectures go into the homework and how to start solving it. In principle, this homework should be a test of what you have learned and at least in the first 5 problems, only use notions from which we have learned already in the lectures. So in that respect, in principle, at least, everything you need is contained in the lectures. The last 4 problems make some use of homotopy theory, which we are just starting to learn today, maybe. So as I said, I'm happy to help you with that. So just let me know. All right. Let me now proceed to what I promised last time, some at least very brief crash course in homotopy theory. What exactly does homotopy theory study? Well, there are many answers, but one of them will be maybe perhaps infinity 1 categories. Infinity 1 categories are categories enriched in some sense in spaces. And so probably the first question we should answer is what exactly is a space in homotopy theory? And another terminology, by the way, for space, of course, is infinity groupoid. These days, the two terms are used mostly synonymously, but it wasn't always that way. But these days, it's always the same. And yeah, so there are many answers. Perhaps the most familiar answer will be topological spaces. And these will be some topological spaces, but you identify weakly topological spaces that are weakly homotopy equivalent.
You mean there when you establish equivalence between definition space and infinity groupoids stable gammatopic hypothesis?
Yes, so not stable. We are not talking about spectra here, but in principle, some of those models could be more naturally interpreted as infinity groupoids. Maybe simplicial sets perhaps could be interpreted in this manner. And of course, the resulting equivalence, for example, between topological spaces and simplicial sets could be interpreted as a version of homotopy hypothesis. But not stable. We are not talking stable yet. All right, so weak homotopy equivalences are just continuous maps of topological spaces that induce isomorphisms on homotopy groups. And here I listed some other answers, all of which were chosen for practical reasons. In fact, in our lectures to talk about functorial field series, we will need all 3 of these. we'll see simplicial sets and smooth sets basically used directly in the definition of a functorial field theory, and small categories will appear in the proof of the geometric cobordism hypothesis if we ever get to it. And they will also appear in some complications of some examples, by the way. And these maps on the right side, they are all secretly just maps that induce isomorphisms on homotopy groups. For topological spaces that was already mentioned, for simplicial sets, which we'll discuss in a second, you can define its own notion of a simplicial weak equivalence, either through geometric realization or directly. For smooth sets, you can define homotopy groups in very much the same manner as for topological spaces, only you use smooth spheres instead of continuous spheres. And finally, there's this really weird model where you model spaces or infinity groupoids as small categories. And this may be perhaps the least intuitive model, but often it is very practical. It's connected to simplicial sets via the nerve functor, and the assertion implicitly contained here is that any space is weakly equivalent to the nerve of a small category. And the relevant notion of a weak equivalence is called a Thomason weak equivalence. Thomason did not introduce this class of weak equivalences, but he did introduce the corresponding model structure. So we'll discuss the last three examples in much more detail a bit later. Let me very briefly address what does the word up to here mean, actually. And maybe one answer is that spaces themselves form naturally not a one category, but an infinity one category. What is an infinity one category? It's a category enriched in spaces. So here we have some sort of a chicken and egg problem, where somehow we said that homotopy theory studies infinity one categories, but in order to talk about infinity one categories, we need to talk about spaces. And in order to talk about spaces, well, we mentioned the most natural way to talk about them will be as an infinity one category, but since this creates a circular reasoning problem, I will talk about spaces first from a naive point of view as a one category, and then we can discuss what should be done to turn them into an infinity one category. All right. All right, let me sort of give you a very brief and practical crash course in simplicial sets. And simplicial sets are a very typical application of the functor of points ideology. If you recall, just like for smooth sets, we have contravarying functors from Cartesian spaces to sets. And the way you would think about such a contravarying functor is that if you have a smooth set, you can map Cartesian spaces into it, and the sets of such maps give you a contravariant functor. Well, the basic reasoning behind the definition of a simplicial set is exactly the same. You should imagine some geometric shape assembled out of simplices. And here I drew a purple example. So you have 0 simplices, which are vertices, a whole bunch of vertices. You have 1 simplices, which are edges, a whole bunch of edges. You have 2 simplices, and let me draw maybe some. For example, imagine this true simplex is shaded. Maybe also this one. So these triangles are present. And simplices in principle are, you allow them to be glued onto themselves. For example, here an edge has the same source and target. And here, for example, a triangle, we collapsed one of its 3 sides and we got a bigone. So 2 vertices of the triangle map to the same vertex here. This is a purely a combinatorial construction in a sense that there is no geometry here. These pictures look geometric, but all what you remember is how different simplices stick together. And when I say how they stick together, I mean every pair of simplices will intercept in some other simplex. And that's the only combinatorial data you remember. So you study such pictures by mapping simplices into them. And in this setting, simplices themselves will form a very simple category called delta. It's called delta because delta looks like a true simplex. Such notations are quite popular in this area of mathematics. Like you also have horns denoted by lambda and cubes depicted as an actual cube. So there's much more than what I indicated here. Even the category theta, the letter theta was chosen to resemble the shape of two cells glued together. So simplices are modeled combinatorially by objects, which by a category where objects are finite, non-empty, ordered sets, totally ordered. So such sets are isomorphic to the set of numbers from 0 to n. And that's how we will typically talk about them. N is any non-negative integer, could be 0, in which case you have a single so its elements of this set are called vertices. So for n equals 0, you have a single element 0, which corresponds to this a single vertex interpreted as a 0 simplex. A set with two elements 0 and 1 corresponds to a 1 simplex. A set with 3 elements 0, 1, 2 corresponds to a triangle. So here I really should have shaded the triangle. The two-dimensional triangle inside is also present. And the last picture we can at least draw in some way will be this 3 simplex, which has 4 vertices 0, 1, 2, 3. And all those triangles should be shaded, and the tetrahedron inside should also be shaded. But maybe I will not shade it just to make not to clutter it too much. There are maybe some observations to make here. As I mentioned, it's a finite order set, and you can see the ordering reflected in the picture by the fact that all edges are oriented from a smaller vertex to a bigger vertex. from a smaller number to a bigger number. And the same here. Always, all arrows go from a smaller number to a larger number. So this produces some internal notion of an orientation of a simplex. Just in case you are wondering how such simplices in our setting are oriented. And just in case you're wondering how this notion of an orientation, why this ordering of vertices is the same as an orientation, imagine this tetrahedron with 4 vertices is an actual tetrahedron in a 3-dimensional space, R3. Then let's fix the vertex 0 as our origin, origin. And then we can look at the 3 vectors from 0 to 1. From 0 to 2. And from 0 to 3. And these 3 vectors form a basis of the 3-dimensional space. And as you might know from linear algebra, an orientation of an n-dimensional vector space can be presented as an equivalence class of bases. So if you have 2 bases, you can declare them to be equivalent if one basis can be deformed into another basis. So a combinatorial orientation of a simplex given by the ordering of its vertices induces a genuine orientation of the corresponding simplex embedded into R3 or Rn in more generally. So the meaning of this contravariant functor is that if X is a simplicial set, then Xn encodes the set of maps from delta n to X. And let me perhaps, maybe we'll make our lecture a bit interactive. So let's use like we did a poll last time. How many of you guys have seen simplicial sets before? So if maybe we can use this reaction feature. So or what is it called? Yeah. So you can click on the green check mark in your reactions if you have seen simplicial sets before. All right, almost everybody. So, okay, I will not go into too much detail. Just let me then very briefly say, just give you a single example. So here is a simplicial set. And I think that's enough. So let me call this X. How do we encode X? So X is a contravariant functor from delta up to sets. and I say x of 0. So 0, recall, is a set with a single. Did I introduce this notation actually? Oh yes, I'm sorry. This is called n in square brackets. So n in square brackets denotes a simplex with n plus 1 vertices from 0 to n inclusive. So x of 0 will be the set of maps, of simplicial sets from delta 0 to x. So delta 0 just denotes the representable sheaf. So this gadget here is just a representable sheaf, omega of 0. That's the traditional notation for the representable functor. And delta 0 looks like a vertex, so here we are going to see maybe 0, 1, and 2 as vertices. Likewise, x of 1 will be the set of maps from delta 1 to x, which is, in our case, you can see already some one simplices in the picture. So let me call this alpha, beta, gamma. But there is more. A one simplex can be mapped, for example, in such a way that its image is just the vertex 0, or any of the vertices, in fact. And these simplices are what is called degenerate simplices. They are obtained by taking a vertex and degenerating it to a map from a one simplex to this vertex. And for example, the map from delta 1 to x whose image lands inside 0, this is called S0 of 0. And likewise for 1 and 2. So in addition to 3 maps that you see immediately in the picture, you also have 3 degenerate maps where you map a one simplex to a single vertex. I think I'll also take care of 2 simplices. Well, we see sort of one true simplex in the picture. This is this Shagig thing in the middle. So let me call it I don't know, sigma. But there is more. A true simplex can be mapped in such a way that its image, say, lands inside one of these 3 vertices. This is called a 0 simplex degenerated twice. And there's even more, because you can also map a true simplex in such a way that its image lands or covers an existing one simplex. For example, here I could have mapped it. Let me pick a different color. Imagine mapping a true simplex to this interval so that this vertex goes to 0 and these two vertices go to 1. So its image will be just a one simplex, but this is one of the elements of our set. So this is denoted by S1 of alpha as 1 because the vertex 1 repeats twice, so you send two different vertices to vertex 1. And you also have maybe S0 alpha. S0 alpha has a very similar picture. Let me draw it on the other side. Where two vertices map to 0 and a single vertex maps to 1. And as you can imagine, you can draw similar pictures for the other three: beta, gamma, delta. And this completes the enumeration of our simplicial set. And of course, if you don't have much experience with simplicial sets, you may be wondering, is it truly necessary to encode these degenerate guys in this picture? Because from the way I drew my pictures, it seems like they are not really participating. And the answer here is that they may be not participating in some contexts, but they are very important in a few other places. And we'll see one of those aspects in just 1 minute. Let me finish this example by saying what happens to the structure maps, right? So you have morphisms in this category. So what happens to such morphisms? For example, the true morphisms from 0 to 1. One of those morphisms sends 0 to 0, and the other one sends 0 to 1. The morphism that sends 0 to 0 is traditionally called D1 because it skips 1. So 1 refers to the element not present in the image. And the other one that sends 0 to 1 is called D0 because 0 is not present in the image. And of course, geometrically, you think of those as sending a vertex to either the initial vertex, or you can send this vertex to the terminal vertex. Two different maps. Now, if we ask ourselves, what does the functor x do to, say, D0 and D1? So let's start with D1. This will be a map from x1 to x0. And here I am abbreviating x evaluated at 1 to x with a subscript 1. And this is a map from edges to vertices. And geometrically speaking, what it should do, it should start with a map from an edge to x and compose it with this map, the map that sends the only vertex here to the initial vertex here. So for example, we can see from the picture that alpha, the edge alpha, is sent to the vertex 0. Beta is sent to the vertex 1, and so is gamma. Right, the initial vertex of beta and gamma is 1. Here's a picture on the left now. Then we can go similar tricks with x of D0. This will be another map from x1 to x0. And now it will be extracting the terminal vertex. For alpha, that's 1. And for beta and gamma, that's 2. The terminal vertex is 2. Yeah, I should have mentioned, so this is D1 and D0 in this picture. We also have, of course, a map between simplices going in the opposite direction. One simplex you can map to a 0 simplex. Both vertices map to the same vertex here. This map is called, yeah, sorry, I should have been a bit more careful because, yeah, sorry, I should have used superscripts here. Now it's, why is it so difficult to, I really don't get it. Yeah, why is this thing erased before? Maybe I should use free eraser. Much better. I should have used a superscript 0 and a superscript 1. Whereas this map here is called D with a subscript 1. And notice X is not present in the notation. That's by design. It's just implicit. I know I should also change all those guys here. Yeah. Sorry about that. And likewise here, this map is called S with a superscript 0. And the map it induces, a structure map it induces is called X of S superscript 0. That's S with a subscript 0. And now we can start computing it. Well, here is a bit tautological because I did not introduce any special notation for degenerate simplices. So for example, you can say S0 apply to the vertex, apply to the vertex, say 0. Well, that will be as 0 of 0, which is in this element of this set. So when you, geometrically speaking, when you have a map from a vertex to X, and you compose it with a map from a one simplex to a vertex, you get the composition will be a degenerate map. Okay, so that's the picture that illustrates how the functor of points interacts with simplicial sets. If you open any of the first generation books on simplicial sets, and there was a bunch of them in the 60s already. There was a book by, well, probably the two most famous ones were by one by Gabriel and Sisman called Categories of Fractions and Homotopy Theory. There is one by May called Simplicial Objects in Algebraic Topology. And there are maybe two less famous ones, which are Curtis, Simplicial Homotopy Theory, and I think Lamotte, which is, I forget what it is. this geometric picture is not mentioned in those books. Which makes it really painful to learn simplicial sets for the first time. But more recently, the situation has improved dramatically, and perhaps these days we can recommend a survey by Friedman, I guess. It's called an Elementary Illustrated Introduction to Simplicial Sets. By the way, pretty much every single bibliographic reference I give you is present on my homepage. The list of literature is my website /reading. So it contains this source and many others. Let me, any questions about this example, maybe I should first ask.
So in this example, we were sort of teasing out the structure maps from just the ordering of the vertices and the fact that we define simplicial sets to be presheaves on the ordinal category.
Yes. So exactly. So the point is like this picture is already sufficiently rich to, like for example, to see that if you have a one simplex that maps to alpha, well, since everything is oriented, you can only map in one way. So its initial vertex goes to 0 and its terminal vertex goes to 1. And this also allows you to compute the precompositions of this map from a one simplex to X with any map to a one simplex. Like, for example, a map from a vertex to a one simplex, you can see that if this vertex maps to the initial vertex, it must map to 0. There is no other choice. So everything is seen completely uniquely from this picture. Yeah.
Right. With the older sources you mentioned, mostly introducing everything in terms of the combinatorial face and degeneracy map relations. So it's like a slew of axioms that it's hard to see this geometric picture from.
Exactly, yeah. So that's why I recommend reading modern sources. I guess another modern source, as a bit of a self-promotion, is my own lecture notes, which also have this perspective. You can find them also on my website. It's called Topology Lecture Notes. Yeah. All right. Let's see. So let me offer maybe very quickly some comments which should address some of the very frequent questions about some choices we made. And one of them we already mentioned. Why exactly do we need degenerate simplices? Like here I said non-decreasing maps, but I could have also said increasing maps. I could have required them to be strictly increasing. in which case I would not see, for example, this degeneracy map that I talked about here, because of course this map sends both vertices to the same vertex here, and that's not strictly increasing, right? It's not injective, which would somehow get rid of all those extra degenerate elements that I went to a great length to enumerate carefully here, like right here. So for example, for true simplices, perhaps you would just see a single element, sigma. And is this not much easier? This would somehow make our life easier. But it can make our life easier in writing down examples, yes, but it makes our life much more painful in other aspects. So such gadgets are known as semi-simplicial sets. And perhaps their main defect is that I should have probably mentioned it a bit earlier. For simplicial sets, well, limits and colimits are computed object-wise. So as you may know, limits and colimits in a functor category are computed object-wise on, if you want to compute the limit or the colimit of a diagram of some simplicial sets, you interpret it as a limit or colimit of a diagram of contravariant functors from delta op to sets. And then the resulting simplicial set will also be such a functor, and its value on some object of delta will be the colimit or limit of a diagram of sets obtained by evaluating the corresponding simplicial sets. So let me maybe write down a formula. Limit of some diagram of sets, simplicial sets xi, where I is ranging in some objects of some category capital I. The n simplices of this resulting simplicial set can be computed as the limit of the sets of n simplices in xi, like this. And in particular, this means that products can be computed object-wise. And let me compute maybe one single product here. Here is a picture of the product of two delta ones, so two one simplices. So I take the product of a one simplex and a one simplex. And in the product, I'm going to see, well, a vertex in the product will be a pair of vertices, one vertex from each factor. So I will have this pair, I will have this pair, I will have this pair, and I will have this pair. Next, a one simplex in the product will be a pair of a one simplex here and a one simplex here. And how many one simplexes do we have inside a one simplex? We have a single non-degenerate simplex and two degenerate ones. Altogether, we have three one simplices. So in principle, we can expect 3 times 3 is 9 one simplices in the product. And of them, 4 will be degenerate because 4 will correspond to pairs of degenerate simplices in each factor. So the 4 degenerate ones will correspond to the 4 vertices here. And what are the 5 non-degenerate ones? For example, I can take the product of this non-degenerate one simplex here, and one of the two vertices, which is the degenerate simplex here. So if I take this vertex, I get this simplex. And if I take this vertex, I get this simplex. Or I can take the product of this one simplex here on top and this vertex. I will get this vertex, this edge here. Or I can take the product of this one simplex and this vertex. I get this edge here. And finally, I can take the pair consisting of this edge and this edge. So both of them are non-degenerate. And geometrically, these edges are precisely the projections of a simplex inside a product. So what simplex has this edge and this edge as projections onto the horizontal and vertical axes? Well, it's precisely the diagonal, right? The diagonal projects to this simplex here and to this simplex here. And so we can see these product of two intervals should be a square, and we do see a square emerging. Likewise, for example, you see this triangle popping up. Its projections onto the horizontal and vertical axes will be two degenerate true simplices here and here. So when you project, say, onto the horizontal axis, this vertex goes here, and these two vertices go to here. So the projection will map a triangle onto one simplex in a degenerate fashion. So you can see how crucial are degeneracy maps that are not injective in encoding products. So for simplicial sets, the product of two intervals will be what you expect, a square, or in general, it looks like a geometric shape you would expect, only triangulated. Here we took two intervals, and the product, of course, is not a square because a square is not a simplex, but it's a gluing of two triangles, which together look like a square. This totally fails for semi-simplicial sets. If you try to write down the same construction, the product of corresponding semi-simplicial sets would look really pathetic. It would look like you would have four vertices. And then for one simplex, you would only have a single one simplex, which will be the diagonal. And that's it. There is nothing else in the product, in the categorical product. Which means that the ordinary categorical product does not compute the correct answer. For example, here we took the product of two intervals and we got something that is not even connected. It's not connected, right? There are three connected components. So it's a totally wrong answer. And of course, if you try to encode desired products in this context, you will have to do something called homotopy products. And whereas previously homotopy for simplicial sets, homotopy products could be computed as ordinary categorical products. Here, you must instead use, let me put it in red, some other model for the homotopy product, which I denote using a superscript H. So this is a cross with a superscript H. You will have to define it separately, and you will have to establish its properties separately. And in fact, you will not even be able to define honest projection maps. So there will be no projection map from the homotopy product to each factor. Instead, you will only see zigzags where one of the legs is a weak equivalence, like here and here. And the reason for that is that, for example, when you take the product of S1 and S1, so S1 and S1 are circles. So S1 looks like a circle. The product of a circle and a circle is a torus, and a torus is a two-dimensional object. It must have at least one two-dimensional cell, which means that there is no projection map from a torus which has a two-dimensional cell onto something one-dimensional, like a circle. So there's just no way to map something two-dimensional to a circle which only has one-dimensional cells, because a two-dimensional simplex inside the torus would have to map in a degenerate way, and in semi-simplicial sets you don't have degeneracies. So things become way, way more complicated for semi-simplicial sets. So, and even though you can prove that the category of semi-simplicial sets is equivalent to simplicial sets, and in that sense, it also encodes a category of spaces. This category is impractical. Yes, you can use it to encode all spaces, but that's not a pleasant or efficient way to do so. Okay, so this explains why we really want degeneracy maps to be present. Any questions about degeneracy maps, by the way? Let me maybe also offer some comments as to why we insist on simplices being ordered. Again, it is possible to discard the ordering, and instead of considering non-decreasing maps, you can literally consider arbitrary maps. So just the category, so delta, the analog of delta will be the category of finite non-empty sets and arbitrary maps between them. This gives you something called a symmetric simplicial set. And these also model spaces. Again, you can organize symmetric simplicial sets into a model category. This model category will be equivalent to spaces. So in principle, that's also a perfectly legitimate model. We prefer not to use it for a couple of reasons that are of a more practical nature. One of them is that sometimes this extra, because ordering need not be preserved, every simplex has a non-trivial group of automorphisms. So you can permute the vertices of some simplex, and you get back the same simplex. So in symmetric simplicial sets, you would have non-trivial automorphisms from delta n to itself, which simply permute vertices. And sometimes, and in fact quite often, it may be annoying to keep track of such symmetric groups. It's extra work, and it's maybe a bit less practical. And the other reason is that in fact, ultimately has the same motivation as the next question, which is, why exactly do we insist that our geometric shapes are simplices and not, for example, cubes, or some working category theory is called cells or globes. So maybe a cube could look like a square, or an honest cube, or a cell could look like something like a bygone or a couple of bygones, or maybe you can also stick them together and so on. In fact, historically speaking, the first developments in abstract homotopy theory were cubical. The first two papers by Kang in the mid-50s were about cubical sets. He used cubes from the in the very beginning. But ultimately, this category has the same it has similar problems with products. Again, products don't work as expected. And you can see it, for example, in if you try to write down the product of the categorical product of two intervals, it's not going to look like a square. And of course, you can try to rectify this problem by introducing a new monoidal structure, which will simply say the product of a P simplex and a Q simplex is a P plus Q simplex. So you would just postulate that a P cube and a Q cube, a P dimensional cube and a Q dimensional cube will be a P plus Q dimensional cube. So there is no way to mess with the categorical construction. You would just say, I have I sort of introduce it by hand, and this would work. But perhaps your life again will become more difficult, because if your product is not the categorical product, then you have difficulty, for example, using the universal property of products, which you would now have to do manually, and that's again really annoying and extra work that you don't want. There's a much more recent modification of cubical sets called cubical sets with connections, where you modify the category of cubes and introduce a map that geometrically looks like you have a square, and you map it to an interval where a single vertex goes to the initial vertex and the other three vertices are collapsed to the target. And such maps are called connections, or sometimes also conjunctions, depending on whose papers you're reading. Conjunction because basically it's conjunction or disjunction in Boolean logic, right? So the conjunction of 0 and 0 is 0, and the conjunction of disjunction of 0 and 0 is 0, and the other three pairs give you 1. And yeah, cubical sets with connections would work, but in principle, I would say they are already more complicated than simplicial sets, so there is no benefit in simplicity here. And there is one more reason why we really want simplicial sets, and this has something to do with practical constructions occurring in mathematics. And the main point here is that objects like monoids or categories give rise to a simplicial object. Every monoid gives rise to a contravariant functor from delta to whatever target category you have. So for ordinary monoids, you would just get sets. So monoids and categories give rise to simplicial sets, and this construction is called the nerve construction, which is what we are going to discuss next. The nerve construction for monoids and categories. Oops. Yeah, sorry. And by the way, until I have moved on, some of the most efficient definitions of homotopy coherent monoids, also known as infinity monoids and infinity categories. In fact, a lot of those definitions start by saying I have a simplicial object and let's impose certain properties on it. And this is a sort of, you can see the construction being reversed, whereas previously you took a monoid or a category and constructed a simplicial object. In the homotopy coherent setting, you can actually go in the opposite direction and define homotopy coherent monoids as simplicial objects with a certain property. Okay, so let me talk about the nerve construction for monoids and categories. And there are, in principle, two notations for something very similar in spirit, capital B and capital N. Capital B is from the bar construction, but personally I would call it D-looping. And you will see why it's called D-looping in a second. And capital N is for nerve. And the way to distinguish between these two constructions is that one of them shifts categorical degrees, and the other one does not shift categorical degrees. So what exactly do I mean by this? You can see for an example, here's one example of a potentially ambiguous construction. If you have a Picard groupoid, which is a symmetric monoidal groupoid with invertible objects, then you can define its D-looping, and you can define its nerve, and these two will be different objects. And the homotopy groups of the D-looping will be homotopy groups of the original groupoid shifted by one, and the homotopy groups of the nerve will be the same as the homotopy groups of G. And this is what I mean by the shift. So categorical degree here is seen by the homotopy group in this context. So for example, pi 0 of a groupoid is just the set of isomorphism classes of objects. And pi 1 is just a group of automorphisms of the monoidal unit. And on the left side, we have certain simplicial sets, and we'll talk in detail how to define homotopy groups of simplicial sets. So let's talk about B first. So B will be a functor from monoids to simplicial sets. Sec is how I denote simplicial sets, so these are functors from delta up to sets. Oh, let's have another vote. If you have seen the nerve construction or the D-looping construction before, could you please select the green check mark, and if you haven't, please select the red cross. So green if you have seen the nerve before, and the red no if you have not in your reactions panel. Okay, so 3 guys have seen it. I guess the rest have not. Everybody is afraid to press the red button. Okay, though I assume only 4 of you guys know it. That means I will explain it in a bit more detail. Yeah, so given a monoid, I'm going to construct for you a simplicial set. And to construct a simplicial set, I have to tell you what sets of n simplices are. And I also have to tell you what the structure maps are. So BM will be a simplicial set. And its sets of n simplices will be as follows. There will be a single zero vertex, there will be a single zero simplex, which is a single vertex in your simplicial set. The set of zero simplices has a single element. Next, the set of one simplices will be precisely the set of elements in capital M. And I depict this, so if I have an element of capital M, let's call it M1, I get a one simplex, which I depict by drawing a one simplex and putting M1 in the middle. So for every element of capital M, I have its own separate one simplex. And at this point, of course, I should have mentioned that since I already said we have a single vertex in our simplicial set, technically speaking, I should have drawn this one simplex as having the same source and target. So what we should really draw is something like this one simplex. But this, if I try to do this consistently in all pictures, this would make those pictures very cluttered and difficult to draw. So I will pretend as if though these vertices are different, even though they are not. They're actually the same vertices. So let me continue to draw those vertices.
As I understand, this assumption is made for simplicity, yes?
Yeah. So this is just to draw pictures that are easier to comprehend. Strictly speaking, I should take all those vertices and forcibly unify them. Yes. Okay, so that's my one simplices. That's my edges. Next, let's talk about true simplices. So here is a true simplex. Such a true simplex has degenerate edges, which we ignore, and it has 3 non-degenerate edges from 0 to 1, from 1 to 2, and from 0 to 2. Now, the edges from 0 to 1 and from 1 to 2 are edges in my simplicial set, and according to the previous description, they have elements of our monoid associated with them. So each of those edges is labeled with an element of our monoid. M1 and M2 are elements in my monoid, capital M. The edge from 0 to 2 is also labeled by an element of capital M. But this element is not arbitrary. It's equal to the product of M1 and M2. And here I reversed the order of product. I mean, in principle, you could have used the other ordering. It doesn't really matter. But the reason I did this is later this product will become composition of morphisms, and morphisms are composed from right to left. Sorry, from right to left. And that's why here I also write the order of factors from right to left. So that's what a true simplex is. So every true simplex will correspond to a pair of elements M1 and M2 inside capital M. And its edges will be as indicated. The edge from 0 to 1 will be M1, the edge from 1 to 2 will be M2, and the edge from 0 to 2 will be their product. And finally, here on the left is a picture of a 3 simplex. A 3 simplex will be likewise specified by a triple of elements M1, M2, and M3 in capital M. And these 3 elements will be placed on the edges from 0 to 1, from 1 to 2, and from 2 to 3. So these 3 edges. The other edges will contain products of these elements. The edge from 0 to 2 will contain the product of M1 and M2. The edge from 1 to 3 will contain the product of M2 and M3, which is placed here. And finally, the edge from 0 to 3 will contain the product of all 3, from 0 to 1, from 1 to 2, and from 2 to 3. M1, M2, M3. So you can see even more generally for simplex of an arbitrary dimension, the edge from the vertex I to vertex j will have a product of all elements from mi plus 1 to mj. Let me draw maybe a picture. I think, yeah, I did mention example, but I didn't draw a picture. So let me draw a picture for you guys. So let's pick some of the simplest possible monoids. So let's say M is a monoid with two elements, 1 and E, and 1 is a neutral element. And E is an eigenpotent. Let's draw the picture of BM. Well, according to what we said before, BM has a single vertex. Now, for every element in capital M, I'm going to have a 1 simplex. So there are 2 1 simplices in the picture. And one of those 1 simplices will be degenerate. So which one will be degenerate? Well, as you have seen already here from this picture, the operation of removing a vertex will multiply elements, which makes use of the multiplication operation in our monoid. But a monoid, apart from the multiplication operation, also has a neutral element which we haven't used yet. And this neutral element, of course, will be taking part in the degeneracy operation. So for example, if I start with my vertex and I degenerate it once, I get an edge, and this edge will have the neutral element as its label. So degenerating some vertex creates new edges, and these edges are going to have the neutral element on them. So the element 1 gives you a 1 simplex, which is degenerate, whereas the element E gives you a non-degenerate 1 simplex. So in my picture, I'm only going to draw a single non-degenerate 1 simplex. All right, next we have to draw pictures of true simplexes. So let's draw some of them.
Please, I don't understand a bit. Since I have seen in some literature that BM is denoted as a classifying space of monoid. Yes.
Yeah, that's the other bit of terminology. So I
Because-
guess I should mention it. Yes, so also in some contexts that's also known as a classifying spaces. Especially if the monoid is a group. Yes.
There we
Yeah.
just denote as a simplicial set, yes? BM.
Here we are constructing the classifying space as a simplicial set. Yes. Yes. Yeah, so in comments, we also have another example why symmetric simplicial sets are not such a good model. They also have additional deficiencies. You can see in chat some hyperlink. All right. Yeah, so this is a construction of the classifying space as a simplicial set. If you want as a topological space, you will take something called the geometric realization of a simplicial set, and you get a classifying space as a topological space. Okay, let's draw pictures of true simplices. So as I said before, a true simplex has elements like this on its edges. And if M1 or M2 are neutral elements, 1, then the resulting true simplex will be degenerate, which we don't indicate in the picture really. So our only choice is that both M1 and M2 to get a non-degenerate simplex will be both of them are E. And then their product will also be E. Okay, and now we have a real problem to draw this properly. So, but what you really should imagine, I have this true simplex, which perhaps geometrically it will be more convenient in your mind to stretch it out to an honest disk with exactly 3 boundary segments. And what is happening now is that we are going to glue this disk to this picture, and all 3 vertices here will be glued to this vertex here. And if, in case this didn't make your life painful enough, each of those 3 intervals will be glued to to the same interval here. And notice also that the arrows indicate in what how to match those two intervals together to this one. So you start here and you move in this direction, and that's exactly how you're going to glue here. Yeah, so this will be fairly painful to draw. In fact, I'm not sure I have enough skills to draw a picture. Yeah, so you can see, however, that simply show sets are in that respect quite powerful because they allow you to encode constructions like this one where a lot of stuff gets glued together. In fact, let me also talk about a small variation of this, where I replace M with a group Z mod 2, which is also has two elements, and the first relation is the same. Did I say something? Oh, yeah, so I meant, this is E, not 1. And this is 1, sorry. Yeah, 1 is a neutral element. I guess in my case, E was a neutral. No, it's sorry about that. So this is E, 1 times 1 is 1, but E is times E will be 1, right? The group Z mod 2, 1 plus 1 equals 0 in the additive notation, or in the multiplicative notation, minus 1 times minus 1 equals 1. And how would the pictures change? Well, the initial stages of the construction will be the same. You still have a single vertex and a single one simplex, but now the true simplex is going to be different. The only non-degenerate true simplex, which will have the non-trivial elements E and E here, and here you will have their product, which is a neutral element. And notice something interesting here. This true simplex, it has a degenerate face, a degenerate edge, but it's not degenerate as a true simplex because degeneration can only produce degenerate edges between consecutive vertices, right? So to produce a degenerate simplex, you would collapse two or more consecutive vertices together, whereas here the edge that is collapsed goes from the initial vertex to the terminal vertex. And these are not adjacent, they are not consecutive in the simplex. So this true simplex is non-degenerate. But its edge is degenerate. Its edge from its edge that is opposite of the middle vertex is degenerate. And so the perhaps a more geometric picture of the same simplex would look like, you would, let me call this 0, 1, and 2. Imagine the edge from 0 to 2 is collapsed. You only have 2 vertices left. And you have this bygone. And you have to glue this bygone to this shape here, which means that both vertices must be identified with this vertex here. And this edge must be glued to this edge, and this edge, I guess I should have oriented the opposite way to make it easier for you guys. Let me orientate it the same way, clockwise. So this edge must be glued to this edge, and also this edge must be glued to this edge. This construction you may be familiar with from traditional topology class. It's called the real projective plane. The real projective plane can be obtained by gluing a disk to a circle where the boundary of the disk is glued to a circle by going around the circle twice. I think it's called like a Guns cap or something like that, some funny name. Yeah, you can see that when we try to classify a space of Z mod 2, something interesting happens. We see that real projective plane emerges in dimension 2. But of course, the construction of the classified space does not stop at true simplices. You're going to see simplices in arbitrary dimension. In dimension n, you will see a single non-degenerate simplex because you only have two elements in your monoid, 0 and 1. And if you pick 0 for any of those, I guess I should have called them M, not alpha, sorry. If any of those mi's is 0, then the n simplex will be degenerate. So your only choice for a non-degenerate simplex is that when all mi are equal to 1. So the classifying space of Z mod 2 has a single non-degenerate n simplex for every n greater than or equal to 0. And that's, of course, known as the infinite dimensional real projective space. A cellular model for the infinite dimensional real projective space is that you have a single m cell for every n greater than or equal to 0. Which you may recognize as a classified space for Z mod 2. In fact, one of the constructions of classifying spaces for groups in the context of topological spaces, you would start with a contractible space like S infinity. The infinite dimensional sphere is a contractible space, and then modeled by the action of Z mod 2, which acts freely on the infinite dimensional sphere by changing, well, by the antipodal map that sends x to negative x. And the result will be RP infinity, the infinite dimensional projective space. Yeah, so we see that the classified space construction is fairly powerful. And any questions about the classified space?
When, for example, if we take monoid and classifying space of monoid S, there are some conditions when they will be weak gamatopy equivalents between each other. Is it possible?
When are the classifying spaces of two different monoids homotopy equivalent to each other?
monoid and his classifying space with Gamatopy equivalence.
Well, okay, there is an algebraic interpretation. For actually, I'll probably mention it somewhere here. For BM is simply the infinity groupoid with a single object.
BM is the user the notion for classifying space, yes?
Yeah, we only define a single BM in this talk, right? The one that we just talked about, right? We can't define any other BMs, right? So this BM, the functor from monoids to sets, simplicial sets.
Okay.
So the algebraic interpretation is an infinity groupoid with a single object, or in other words, it's an infinity group where the group is a group of automorphisms of the single object. And what is the infinity group? Is what you get when you check M and invert all elements in M up to homotopy. So that's known as the homotopy group completion of M. So the classifying space, when interpreted as a simplicial set up to a weak homotopy equivalence, encodes the homotopy group completion of M. So your question, when is M weakly equivalent to its classifying space? Or more precisely, we should probably say when is the d-looping of M weakly equivalent to its classifying space? Or perhaps when is M weakly equivalent to the loop space of its classifying space? Pick your favorite presentation. This question amounts to asking when is a monoid weakly equivalent to its homotopy group completion, or in other words, basically this amounts to asking when is the homotopy group completion of M, which a priori is an infinity group, when is an ordinary group, a group that is just an infinity group, but which is equivalent to an ordinary one group. And in general, that's it can be a difficult question with no single good answer. And there are criteria to prove this in some cases, but it's definitely not always true. And there is no single all-encompassing criterion that will tell you when exactly it's true.
Group completion for monoid is a loop space of classifying space, yes?
Yeah, for example, yeah, so more concretely, you can say homotopy group completion is a loop space of BM. Yes. Yes.
We need to impose condition that P0 grow P0 group is a group. P0 of M is a group. To impose such condition.
Well, pi zero of a well, after you do homotopy group completion, is always a group. Because the loops of something will give you a space which has as a pi zero, it will always have a group, right? Because loops can be composed, and this specifies a group operation. But M itself need not be a group. So of course, being a group, yeah, I guess, yeah, so I said maybe something very stupid. If you have a monoid that is equivalent to its homotopy group completion, then of course, this monoid is already a group. So in this case, nothing is happening. So it's always, a group is always equivalent to its homotopy group completion. However, it is possible to have monoids that are not groups whose homotopy group completion is an ordinary group, and it is also possible to have monoids that are not groups whose homotopy group completion is an infinity group that is not an ordinary group. So in some cases you can get higher homotopy groups, and in some other cases you don't get higher homotopy groups. But if you start with a monoid that is already a group, then you don't get anything new. You just see the same group back. So if G is a group, or M is a group, then the canonical map from M to omega BM is a weak equivalence.
For any topological group, yes? Is it true?
Well, here we only talk about classifying spaces of ordinary groups. We haven't talked about classifying spaces of simplicial groups yet. But in principle, I guess once you extend the construction to simplicial groups, you can say exactly the same thing, yes. All right, so any more questions about the nerve construction? Okay, so I guess this may actually be a good point to stop, because that's a nice logical breaking point. And please don't forget, we don't have lectures the next week or the week after that. So our next lecture will be on January 7th. And also, there is a Christmas present for you guys posted on the website. The homework, the first homework, it has 9 problems in it. And feel free to discuss those problems between yourself and also ask questions. So by the way, we have a Discord, perhaps which you can use. Everybody, I think, should have access to a Discord, but if not, you can either email me or one of the participants whom you know. All right.
So I guess I have one quick question, Dmitri, on the just on the notation in the homework.
Oh yes, of course.
Just wondering exactly how I'm supposed to think about the set of smooth maps from this Cartesian space to a Lie group. G when it's
But-
described as an automorphism group. Sorry, how is that set of maps a group? What's the operation I'm supposed to be thinking of?
Sorry, which problem are we talking about right now?
This is just the bullet point for BG under notation.
Yes, so this one?
Right. Yeah. So how is C infinity from S to G? How am I supposed to, what's the group operation?
Yeah, so the group operation, yeah, G is a Lie group.
Right.
So the group operation here is pointwise. You have two
Oh,
functions,
right.
while in G and the group operation is pointwise.
Got it. Okay. Thanks.
Yeah. So as I said, in principle, at least for the first 5 problems, what we have learned in the lecture so far should be sufficient to solve them. But of course, you are welcome to talk to me or discuss it on Discord. In case you are totally lost, for example, and don't even know where possibly you could start. I could provide you a reference for the first problem just in case. But in principle, like all of these things, you should be able to compute now. And if not, just ask me.
Okay. Do you want to, I mean, not to put anyone on the spot or sort of sign other people up for presentations, but is there at any point some reason for us to maybe like present solutions or something?
Yeah, absolutely. We can have like a session. Like if you guys can present stuff, solve some problems, then you are welcome to present it. Yes. Yes. In
Okay.
fact, that would be the desirable outcome.
I think that could be fun. Yeah.
Yeah. And as I said, do feel free to discuss it on Discord or any other platform you can find, and talk to me or email me. Yeah. All right. Any more questions? Okay. All right, then I guess that's it for today, and that's it for this year. And I hope I see you guys next month, next semester. We can have